A-Level Paper 3, Specimen Set 2. Paracetamol is a common analgesic used for pain relief. It's got the structure shown below. The melting point is 170. Paracetamol can be prepared from the reaction between 4-aminophenol, and it's given you that, so it looks as if it's a benzene ring with an OH at one point and an NH2 at the other point. So it's got an OH there, it's got a benzene ring, and it's got NH2 there, and ethanol chloride. So it's all of this part here with an NH2, and then ethanol chloride has added this little bit on at the end. Write an equation for this reaction. So you need OH C6H4NH2, and then ethanol chloride is CH3COCl. Okay, and then what's actually going to happen is that this part here, the NH2 bit, is going to lose an H, and then the COCH3 is going to come on here, COCH3, and it's going to release hydrogen chloride gas, a toxic gas. That's what makes this dangerous and highly exothermic in terms of its reactions. Name and outline a mechanism for this reaction. Use R and H2 to represent 4-aminophenol. So you've got this NH2, remember it's got a lone pair of electrons on its NH2, and it's going to react with the lone pair of electrons on the N. Is going to attack that C there because that's got a delta plus on it due to the delta minus on the O and the delta minus on the Cl. However, it's an addition elimination reaction, because what actually happens is that N with its lone pair bonds to that C, and the electrons go onto the O. First of all, the Cl is not released immediately, the electrons go onto the O, and then the N will get a plus charge because it's had electrons move away from it. The lone pair of electrons on the O's got the minus, by the way, as well. The O's got a minus, electrons moving onto it has got a minus, but it's the lone pair of electrons that move back into the bond. The Cl is then released, and one of the hydrogens puts the electrons from the NH bond onto the N+. So that's then going to make the Cl will have been released as Cl-, it'll create a C2 oxygen double bond, CH3 and NHR, and this bit is the phenol bit, the benzene ring and the OH. It'll make H+, Cl-, and that will make HCl, the toxic gas. Question 1.3. Paracetamol formed is impure. It contains impurities that must be removed by recrystallization. A suitable solvent. Well, the paracetamol should dissolve when the solvent's hot, but not dissolve when the solvent's cold. So when it's cold, it doesn't dissolve, but when it's hot, it is. That's the paracetamol that we're trying to make. The impurities should either be insoluble in the solvent at all temperatures, or soluble even in cold solvent. When a hot saturated solution of paracetamol is cooled, as much product should recrystallize out, so we should be able to cool it down and get the paracetamol out, leaving the insoluble purities in the solution. The solvent's been suggested, it's flammable, it's got a boiling point of 80. Outline how you carry out an investigation to show that the solvent is suitable for the recrystallization of the impure paracetamol. Include practical details, and then explain how you'd check that the recrystallization process had been effective at producing a pure sample. So first of all, we've got to work out whether this solvent's suitable or not. So let's just remind ourselves, the paracetamol should dissolve when the solvent is hot, but not dissolve when the solvent's cold. And then when we cool it down, we should get the paracetamol back out again. It's a flammable liquid, it's got a boiling point of 80. Okay, let's have a look then. So we take a small amount of the paracetamol, put it in a test tube, add a small amount, just a small volume's fine, you don't need to say how much, of the cold solvent. So we want the solvent cold. It says that when the solvent's cold, the paracetamol should not dissolve. So let's give it a shake or a stir just to make sure, and if the paracetamol does dissolve, then the solvent is unsuitable. Okay, so we're checking out whether the solvent's suitable or not. Then you heat it. We're going to heat it on a water bath to less than 80 degrees C. Water bath because it's flammable and it'll set on fire. We heat it with a Bunsen, and it's got to be less than 80. We don't really want it to boil and start to evaporate. At this point the paracetamol should dissolve. So if the paracetamol doesn't dissolve, the solvent's unsuitable, the paracetamol should dissolve. If the paracetamol dissolves partly, then you can add a bit more solvent just to make sure that it does dissolve, and if it does dissolve, then the solvent's fine. Then you cool it in an ice bath and you hope the crystals will come out. We're hoping that the crystals, as much product should crystallize out. So we're hoping that the paracetamol crystallizes out when we cool it down in an ice bath, and if it does, then it's probably a suitable solvent. How do you check if the recrystallization has produced a pure product, a pure paracetamol? Then you determine its melting point. If it's a sharp melting point close to the data book value 170, but you don't need to know that, a data book close as possible to the data book value, then it's going to be pure. When paracetamol is prepared by reacting in excess of 4-aminophenol with ethanol chloride, the expected percentage yield is 65%. Then, after recrystallization, a further 20% of the impure product during recrystallization. So 20% of that product that you've just got out, 20% of the 65, will probably be lost. A student started with 3.87 grams of ethanol chloride, so we could work out the number of moles of that. After preparation, followed by recrystallization, the student actually obtained 4.07, so we could work out how much they should have made. Calculate the mass of impure paracetamol expected from this experiment based on 65% yield, and then say whether the student had demonstrated expert practical skills. So first of all, we've got 3.87 of ethanol chloride. We can work out the MR of ethanol chloride because it's CH3COCl. So CH3COCl, MR should come out as 78.5. Moles is mass divided by MR, so moles is 3.87 grams divided by 78.5, 0.0493 moles. Now we want to find out about the paracetamol, see how much we should have made. Well, from the equation back at the beginning of the question, it tells me that 1 mole of ethanol chloride produces 1 mole of paracetamol. So if I've got 0.0493 moles of ethanol chloride, I should make 0.493 moles of paracetamol. Now I know the MR of paracetamol, or I can work it out as 151, so the moles equals 0.493, which equals the mass divided by MR. 0.493 equals mass divided by 151. Multiply the two numbers together and it tells me that I should make 7.44 grams of paracetamol. That's assuming that's 100% yield, assuming that everything works perfectly. That's my theoretical yield. So what would 65% be? 65% would be 65 divided by 100 times 7.44, 4.84 grams. That's what I should make. That's what 65% of the theoretical yield is. Now what the actual student actually made, what she or he made, was 4.07 grams, and that was after recrystallization. So after preparation followed by recrystallization, the student actually obtained that. So let's work out how much they lost during recrystallization, because it's this process of recrystallization which will determine whether the student has demonstrated expert skills. So let's work out how much this person lost. So they lost 4.84, that's how much they should have made. Take away 4.07, they lost 0.77 grams. So they could have made 65% of the product was 4.84 grams. They made 4.07 grams. So during recrystallization, they lost 0.77 grams. Okay, they lost 0.77 grams out of the 4.84. So I wonder what percentage that is. If they've lost 0.77 grams out of the 4.84 that they've made, 65% of the yield that is, times by 100, 15.9%. So this suggests that the student has demonstrated expert practical skills because it's less than the 20% that was expected. Suggest why the student should not use this sample of paracetamol for the purposes of pain relief. It's probably got impurities in there. may still be amounts of impurities, suggests two reasons why in an industrial situation ethanoic anhydride would be preferred to ethanol chloride in the production of paracetamol. Well, ethanol chloride actually undergoes violent reactions. It produces very exothermic reactions, violent exothermic reactions that give out a lot of heat. And it's very difficult to control that heat. It reacts with water to make hydrogen chloride gas as well, which is a toxic gas, and it's quite expensive as well, ethanol chloride, compared to ethanoic anhydride. So ethanoic anhydride, easier to control the reaction, less exothermic reaction, less heat given out. A dangerous toxic gas is not produced with ethanoic anhydride, whereas it is with ethanol chloride. The dangerous toxic gas is hydrogen chloride. And also allow ethanoic anhydride is actually cheaper than ethanol chloride. Question 2. We've got an esterification reaction between ethanoic acid and ethanol to make ethyl ethanoate, an ester which has got a CO linkage in there and water. Write an equation, so CH3COOH, CH3CH2OH, makes ethyl ethanoate, which is going to be CH3COOCH2CH3 and water. Draw the skeletal formula of ethyl ethanoate. Well, before you draw a skeletal formula, I would always draw this out. So I'd always draw it out and see what it looks like. CH3COOCH2CH3. I would always draw that, and then you can draw out the skeletal formula. So you put the C's as dots or just corners on a zigzag line. Remember the carbon backbone is in a zigzag line. You leave the hydrogens off and you draw the O's. So it'll look a little bit like this. So you've got CH3, you can put that up or down, doesn't really matter. The CO next, that can go up or down based on where you've put the methyl group. So this is the methyl group up and the CO down. You could have it the other way around if you wanted to. And then come along is an O and then a CH2CH3. So we just show that by a kink in the chain. So there's the CH2 and there's the CH3 at the end. The student used a small amount of concentrated sulfuric acid to act as a catalyst. How does the catalyst work? Well, it provides an alternative route or mechanism for a reaction, and therefore, by doing so, lowers the activation energy. Catalyst provides an alternative route for a reaction or mechanism. Same thing, both are allowed. This lowers the activation energy. A student mixed 0.435 moles of ethanol and 0.435 moles of ethanoic acid, and then used 5.00 times 10 to the minus 4 sulfuric acid in the mixture as well. The mixture is left for a week to reach equilibrium. The equilibrium reaction was stopped by adding the mixture to water. The Kc, the equilibrium constant, was 4.07. Calculate the volume of 0.4 mole dm to the minus 3 sodium hydroxide required to react completely. This is a tricky question. Very, very tricky indeed. So let's have a look at the solution. Let's see if we can talk it through. So what you've got is the mole. I've written out the equation, and then I always do a table. I always do moles at the start and then moles at the end and then left over. So I've got moles at the start, 0.435 moles of ethanol, 0.435, same amount of ethanoic acid, and I haven't got any ethyl ethanoate and I haven't got any water produced. Now, it doesn't tell me how much ethyl ethanoate and water I make, so I'm going to call that X. Now, 1 mole of ethanol reacts with 1 mole of ethanoic acid to make 1 mole of ethyl ethanoate and 1 mole of water. So whatever amounts I make, X, that's the amount that's used up. So if I had 0.435 of this at the start, I've used up X amount, X number of moles of this to make X number of moles of ethyl ethanoate and X number of moles of water. And similarly here, I've used up X amount of those. Now if I've got my equilibrium constant, which equals 4.07, and it's the concentrations of the product divided by the concentrations of the reactants that looks like that, then the concentrations of each of these are X, so that's X squared, divided by 0.0435, take away X, and it's the same in both cases. Then if I square root everything, I'm allowed to do that. If the square root of everything, square root of 4.07 equals the square root of x squared, which is x. The square root of 0.435 take away x squared. The square root of that again is 0.435 take away x. So I've just removed the x squareds. 2.017 is the square root of 4.07, and then I've multiplied by this value of taking it from the bottom on one side to the top on the other. 0.435 take away x equals x, and multiply 2.017 by 0.435, and it ends up as 0.878. Take away, you've got to do times by x as well. 2.017x equals x. Take x from one side to the other, it's minus on this side, it'll be a plus on the other. 0.878 equals 3.017x. Divide by 3.017, it'll give you x, 0.0291 moles. I now know how much of this I have made in the mixture. So, I can work out what's my acid, where's my acid, because it's saying work out the amount of acid that's in the mixture. Well, the ethanoic acid left at the end, 0.0435, take away 0.0291, I've got 0.0144 moles of acid left at the end. I also added some sulfuric acid, 0.0005 moles. But remember, 1 mole of sulfuric acid makes 2 moles of H+. It's a diprotic acid. So number of moles of H+ made equals 0.001. 0.0005 times 2 is 0.001. Now, so I've got that amount of sulfuric acid, 0.001, and I've got 0.0291 moles, 0.0144 moles of ethanoic acid. If I add the two together, I will find out that I've got 0.0154 moles of acid altogether from the sulfuric acid and from the ethanoic acid at equilibrium. Now that I've got a number of moles of acid, the number of moles of sodium hydroxide to react with the acid is the same. 1 mole of sodium hydroxide will react with 1 mole of acid. So concentration equals moles divided by volume. Concentration is 0.4, that's from the question. 0.154 is the number of moles of sodium hydroxide divided by the volume. Rearranged to get the volume is 0.00154 divided by 0.4. It equals 0.00385 decimeter cubed. Now it says it wants in centimeter cubed, so to turn decimeter cubed, a larger unit value, into centimeter cubed, I multiply by 1000, so it turns out to be 38.5 centimeter cubed of sodium hydroxide that I need. Question 2.5. Explain how the student could check that the mixture had reached equilibrium after 1 week. Well, after 1 week you take some samples and then you take some further samples in the forthcoming days to see if the concentrations of the reactants and the products had changed. If they hadn't, then you'd know that it had reached equilibrium. The concentrations of the reactants and products don't change at equilibrium because the forward and backward reactions are at the same speed, at the same rate. Question 3. EDTA is a useful laboratory chemical found in a wide variety of commercial products, including detergents, very soluble in water, and is often used in its ionic form. EDTA 4- is shown below. Explain means the term multidentate ligand with reference to the reaction of EDTA 4- with copper, hexaaquil copper 2 ions. Draw in figure 1 a separate circle around each atom that bonds to the Cu2+ on the complex ion. Well, remember, the central metal cation, plus ion, has ligands bonded to it, and the ligands use their lone pairs to form bonds, to form covalent bonds. They use both lone pairs to put into the covalent bond. It's a normal covalent bond, except that the lone pairs have come from one of the atoms rather than both atoms putting 1 electron each. a pair of electrons, a lone pair of electrons, has been provided by one of the atoms to form that covalent bond. That covalent bond, that special covalent bond, where both the electrons have come from one of the atoms rather than one electron from each of the atoms, joining together in the covalent bond, is called a dative bond or a coordinate bond. Anyway, we're looking for atoms with lone pairs of electrons that might form dative or covalent or coordinate bonds with the Cu2+, and the answer are the nitrogens and the single oxygens as well. The single oxygens probably carry the negative charge and have lots of lone pairs of electrons on them. Multidentate means that the EDTA can form many dative bonds with the central cation, the central plus charged ion, so it can form 6 bonds. Those 6 atoms can form 6 bonds, many dative bonds, so they're covalent bonds where both electrons have come from these atoms here that are circled, rather than one atom putting an electron in each to form the covalent bond. Both of the electrons have come from these atoms, and they bond into the central cation. A cation is a plus ion, the central Cu2 plus ion, plus charged ion. The ligand has a lone pair, say for example on the O and the N of EDTA, which can form a dative bond with copper 2 ions. Question 3.2. Copper 2 compounds can be used as fungicides in vineyards. When they use the copper 2 ions, enter the water supply and cause problems because they're toxic in high concentrations. The water supply near a vineyard can be tested for copper 2 ions by forming a blue aqueous complex with EDTA 4- ions. The concentration of this complex can be determined using a colorimeter. What a colorimeter is, you take a sample of the liquid and you shine a light through it, and depending on how coloured it is, it will tell you how much of the light passes through, and you can determine the colour. The one thing is it needs calibrating because you're never quite sure. You want to be able to see the light reading coming through and then determine the concentration of the EDTA. So we'll have a look at how you can do that now. You calibrate a colorimeter, means set the scale or the readings correctly, and so what you do is you test the colorimeter with solutions of copper and EDTA complex of known concentrations. So you get the complex ion of a known set of concentrations, and then you take the reading on the calorimeter, and then you can add lots of EDTA, excess EDTA, to the sample to ensure that all the copper 2 is used up, because you want to determine the concentration of copper 2. So you make sure you add too much excess EDTA so that all the copper 2 in the sample is used up, and then test with the colorimeter and compare to the readings of the known concentrations. The concentration of copper 2 ions in the sample of water by calorimetry was determined to be 7.56 times 10 to the minus 6. This result was checked by titrating a sample of the water with a solution containing EDTA ions. The EDTA 4- ions used in the titration had a concentration of 1 times 10 to the minus 3. So you did a titration just to double check. Write an equation for the reaction between copper H2O6, so it's got 6 ligands around it, 2+, and EDTA 4- ions. Well, we know that an EDTA 4- ion actually has 6 different ligands. So we've got 6 waters, each with 1 dative bond, but this EDTA produces 6 dative bonds. So that EDTA can replace all of those 6 waters. So it'll look like that. CuH2O6 forming 6 bonds, EDTA can do it as 1 bond, so you've got Cu EDTA, and the 6 water molecules come off the 6. Now you just need to check what charge is on here. EDTA is a 4-, water's nothing, so copper's 2+, so copper 2+ and 4- would leave 2 left over. And you can check that against your charges here. 2+ and 4- leaves 2- left over on the left, 2- left over on the right. So let's have a look what we need to do. So the concentration of copper ions is 0.0000756. So we've got that from here. Okay. So the volume that we've got, the volume of the water sample is 25 centimetre cubed. To turn 25 centimetre cubed small units into larger units, you need to divide by 1,000. So 25 divided by 1,000 is 0.025. So the concentration of copper ions is this: concentration equals moles divided by volume, moles divided by 0.025, and therefore the moles of copper ions are the two multiplied together and equals 0.000000189. So that's the number of moles of copper ions. So the number of moles of copper ions in there equals the number of moles of EDTA ions. Look, 1 copper, 1 EDTA. So 1 mole of EDTA reacts with 1 mole of copper ions. We know we've got this number of copper ions, so we must have this number of moles of EDTA. One thing it does want to work out is the concentration of EDTA. Concentration of EDTA equals 0.001. So it tells you that here, 1 times 10 to the minus 3. So the concentration of EDTA equals 0.001. 1 mole of EDTA reacts with 1 mole of copper ions. We've said that already. So we've got 0.000189 moles of EDTA. Concentration of EDTA equals 0.001. So there's the concentration, which equals number of moles 0.00000189 divided by the volume. We can take this value here and divide by 0.001. So 0.00000189 divided by 0.001 equals 0.00189 decimeter cubed. It's in decimeter cubed, and therefore you can multiply by 1,000 to get in centimeter cubed. So to go from a large unit value down into a smaller one, you multiply by 1,000. This is too small to provide an accurate solution. Justify whether this titration will give an accurate value. It's too small really. 1.89 is way too small to do a titration with, and so what you need to do is you need to dilute the EDTA so that you get same amount of moles but in a larger volume, so when you run it out of the burette you get a larger volume coming through, and then that will be easier to read from the burette. Question 4. I've got a reaction between iodine, propanone in the presence of an acid catalyst according to this equation. I've got different mixtures, A to E, prepared. And it tells me how much iodine, sulfuric acid, propanone I've got in there and how much water. Calculate the initial concentration in moles per decimeter cubed of propanone in mixture A. Let's have a look in mixture A. Mixture A, propanone is here. I've got 25 centimeters cubed and I've got 1 mole per decimeter cubed. So I can use that first of all. So the volume is 25 centimeter cubed, divide by 1,000 to turn smaller units into bigger ones, like centimeter cubed into decimeter cubed, 0.025. Concentration equals 1. It tells me the concentration of propanone equals number of moles divided by volume. So 1 equals moles divided by the volume is 0.025. So moles are these two multiplied together. 1 times 0.025 is 0.025. So that's number of moles of propanone that I've got, 25 centimeter cubed, 1 mole per decimeter cubed. 0.025 moles of propanone in here. However, I'm mixed with other things. So I've got that number of moles, but my total volume is 40. Add 25, that's 90. So I've got 90 centimeter cubed in total, and that's what it wants me to work out. What's the concentration in the whole total amount? Well, 90 centimeter cubed into larger decimeter cubed, you divide by 1,000, so that's 0.09. Concentration equals moles divided by volume. We know that, so 0.025, which is the number of moles, divided by the volume, 0.09. As the volume equals 0.278, and that's the concentration. State and explain why different volumes of water are added. So we want the same number of moles of propanone, the same concentration of propanone, the same number of I want to change the concentration of propanone but keep the total volume the same. So I want to keep the total volume all the same, so it's a fair test in that respect, but I want to change the volume of propanone and hence change the concentration of the propanone. Question 4.3. Calculate the volume of 0.100 mole decimeter cubed sodium thiosulfate solution required to react with all of the iodine in a 10 centimeter cube sample of mixture E before the iodine reacts with the propanone. So first of all, let's have a look back and let's have a look at the amount of iodine. So in mixture E I've got 40 centimeter cubed of iodine. There's my iodine, I2, 40 centimeter cubed, 0.02. So 40 centimeter cubed, I've got to get into decimeter cubed, so I divide by 1000 to get a small unit like a centimeter cubed into a decimeter cubed. 0.04 decimeter cubed. Its concentration of iodine is 0.02. So concentration is moles divided by volume, so 0.02, which is the concentration, equals moles divided by 0.04 decimeter cubed. Multiply the two together, so the moles of iodine in the sample is in the mixture is 0.0008. Now then, the total volume is 40, add 25, add 6.5, add 18.5. That's the total volume of the mixture of E, which is 90 centimeter cubed. So the total volume is 90 centimeter cubed. So I've got 0.0008 moles of iodine in 90 centimeter cubed of mixture. It says I'm going to take a 10 centimeter cube sample of the mixture. So if I've got 0.0008 moles of iodine in 90 centimeter cubed, I've got to work out how much iodine I've got in 10 centimeter cubed. So divide by 9, or you could say out of 90 centimeter cubed, I divide by 90 and then multiply by 10. So I've got to work out that I have 0.000889 moles of iodine in a 10 centimeter cube sample of mixture E. Instead of 90 centimeter cube total, I've now worked out how many moles I've got in 10 centimeter cube sample. From the equation then, 1 mole of iodine reacts with 2 moles of this sodium thiosulfate. So 0.000889 moles of iodine in the 10 centimeter cube sample would react with twice the number of moles of sodium thiosulfate. So I'll multiply by 2, 0.000178 moles of sodium thiosulfate are going to react with the iodine. Concentration equals moles divided by volume, so I've got moles. I've got the concentration here is 0.01 of the sodium thiosulfate. So concentration of the sodium thiosulfate 0.01. Moles of the sodium thiosulfate that I need is 0.000178 divided by volume. So the volume equals 0.000178 divided by 0.01, once I rearrange that equation, equals 0.0178 decimeter cubed. It asks for it in centimeter cubed somewhere, so 0.0178 decimeter cubed multiplied by 1000 is 17.8 centimeter cubed. So question 4.4 wants me to draw a graph. It's got time in minutes across the top and the volume of sodium thiosulfate needed to react with the iodine in a 10 centimeter cube sample of E. It doesn't really matter, it just wants me to plot these graphs, and it says to plot a graph of volume up the y-axis up here, and it wants the time along the bottom. So let's have a workout. We've got to cover at least half the graph paper. So maybe you could put a little squiggle a little squiggle, a little break at the bottom there, and we can start here at our lowest value of V, which is 16, and then maybe every 5 little squares that could be 0.1. Let's see how high that would take us. So we put a little break there like that and go 16, 16.1, 16.2, 16.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 17, 17.1, 17.2, 17.3, 17.4 and 17.5 takes us perfectly to the top, and along the bottom I want to go 5, so 0, 5, 10, 15, 20, 25, 30 along the bottom. Okay, and that's perfect. So what do you get your marks for? You've got to cover at least half the graph paper, which we did. You've got to put you've got to label both of your axes. Must have a scale on them, so they've got to be to scale. Actually, you don't get a mark for the axes, but it's just good practice for labeling them. But everything's got to be to scale, so you've got to go up by the same sort of increments. So you don't go up 5, 10, 20, 30. Say, for example, you don't go 5, 10, 20, 30. You go 5, 10, 15, 20, 25, 30. So incrementally each time you're going up by the same amount. So got to have a reasonable scale. Best fit line should be drawn, and then you work out the gradient. If you work out the gradient, which is the change in the y-axis divided by the change in the x-axis, it should come out as 0.060, and it'll be a minus value because it will be coming down. 4.5. The gradients for similar graphs produced by mixtures A, B, C and D are shown in table 3. So we've got some similar gradients. Each gradient is a measure of the rate of the reaction between iodine and propanone for each of the mixtures. Use your information in table 1 and table 3 to choose the order with respect to propanone. Explain your answer. So what you've got is the gradient, the rate of the reaction. If it's a straight line, then the reaction is first order. So the previous one was a straight line, and so if it's a straight line, it shows that the reaction is first order, and it's as simple as that. Each sample taken with the reaction mixture is immediately added to an excess of sodium hydrogen carbonate before being treated with sodium thiosulfate solution. Suggest the purpose of this reaction. Well, sodium carbonate or sodium hydrogen carbonate reacts with acid, and the acid is catalyzing this reaction. So if it reacts with the acid, it prevents the catalyst from working and stops the reaction. So it stops the reaction at that time, so that you know you can measure the concentrations at that time, because you've stopped it effectively by removing the acid catalyst. Question number 5. What are the numbers of neutrons and electrons in a 57 Fe2 plus ion? So it's lost 2 electrons to become 2 plus. So if you look it up in the periodic table, the atomic number is 26, 57, its mass number. So the numbers of neutrons are 57 take away 26, which is 31. So it could be either A or C. And it's had 26 electrons, but it's lost 2 electrons to become 2 plus, so it's got 24. So your answer is A. Which of these contains the most number of molecules? We've got masses, and we've got the formula of each, so we can work out MR, and we can work out the number of moles of each. So we could then, the number of molecules is the number of moles multiplied by Avogadro's number. We could multiply each of them by Avogadro's number, but we're kind of doing the same thing to each of them. So whichever is the most number of moles is also the most number of molecules. We don't actually have to calculate the number of molecules to work out which would be the most. So whichever one's got the most number of moles, when we multiply by Avogadro's number for each of them, that would also give the largest value. So I'm going to work out the number of moles of each. Moles is mass divided by mR. I've got to get the masses into grams first of all. So let's have a look at A. 0.311 kilograms. Well, to convert kilograms into grams, a large unit value into a smaller one, then I'm multiplying by 1,000, so that's 31.1. The MR of CO2 is a 12, add 2 16s, which is a 44. Number of moles is mass, 31.1 divided by 44, 0.707. B, 29.6 grams of carbon monoxide, that's a 12 and a 16. So number of moles is 29.6 divided by 28, which is the MR. A 12 add a 16 is 28. 1.5057 is the number of moles of carbon monoxide. Milligrams into grams, so small into large. And so a small into larger, so I want to try and get it into grams. Small into large is divided by 1,000, so I've got 2.22 times 10 to the power of 4, 2.22 times 10 to the power of 4, 2,220 milligrams. Then I divide by 1,000, which is 2.2 grams. So to get milligrams into grams, small into large, I divide by 1,000, 2.2 grams. The MR of oxygen, O2, is 2 16s, for 2 oxygens, 32. So the number of moles is 2.2 divided by 32, which is 0.0688. And then finally for ozone, which is O3, I've got it in grams already, so it's 13.3. O3, 3 16s, 48, 13.3 divided by 48, 0.277. The largest value is 1.057, so if I were to multiply each of these by Avogadro's number, this one would still give the largest one. Answer B. Question 7. Which of these statements best describes a dative covalent bond? So that's where you've got a normal covalent bond between two atoms, but instead of one atom putting one electron in each and the other putting another electron in, and then both putting one electron in each, one of the atoms puts both of the electrons in. So which one's this? A pair of electrons shared between two atoms where one atom has donated one electron. No, that's wrong. A pair of electrons shared between two atoms where one atom has donated 2 electrons, both electrons. The answer is B. Which molecule is the least polar? We've got bromomethane, 2-bromomethane, dibromomethane, tribromomethane, where we've got 3 bromos on there and 4 bromos on there, tetrabromomethane. Well, the answer is D, because tetrabromomethane means that the polar bonds, the delta plus and delta minuses, cancel out in all directions because it's symmetrical. So there's no permanent dipole set up because of the symmetrical nature of all of the delta plus and delta minuses, all the polar bonds, is they effectively cancel each other out. Question number 9. Which statement about intermolecular force is not correct? Intermolecular force exists between all simple molecules. Yes, even if it's just simple van der Waals forces, then they exist. So A is correct. Hydrogen bonding occurs between HBr molecules. No, you only get hydrogen bonding when you get a hydrogen to an oxygen, a hydrogen to a nitrogen, a hydrogen to a fluorine, and you get a large difference in electronegativities, so you get a large polarity, a large delta plus and delta minus, a large polar bond, and then the intermolecular bonds are strong between those large polar bonds in each of the different molecules. So B is incorrect. Let's just check though. Hydrogen bonding is the strongest intermolecular force in liquid ethanol. Yes, hydrogen bonding is always the strongest intermolecular force, and ethanol does have an oxygen bonded to a hydrogen. Hydrogen bonding occurs between CO and HN in proteins. Yes, that's true, because you've got a hydrogen bonded to a nitrogen. Anywhere where you've got a hydrogen bonded to a nitrogen, a hydrogen bonded to an oxygen, a hydrogen bonded to fluorine, you've got hydrogen bonding. So the answer is B. For the next one here, I've got a reaction here, and I'll just do spoilers on this one so you can see what's happening. We've got the enthalpy of formation. So we're forming C2H6, we're forming 6F2, we're forming C2F6, and we're forming 6HF. when you form things from their elements in their standard states. That's how you normally find them in the laboratory. Carbon is a solid, fluorine is a gas, and hydrogen is a gas. So they're being formed from these things here. And when I form the C2H6 here, it says it's minus 84. So I'm forming it from the elements in their standard states, and I'm making this minus 84. Fluorine is already in its standard state, F2. That's as you normally find it, just a normal element. It's not combined with any other atoms, so I've not actually had to make it at all. So the enthalpy is 0 for that. To make C2F6, then it's minus 1334 here. And to make 6 lots of HF, I don't know. That's what I need to find out for HF. Now then, they're coming from here, and they're coming round to here. So they're coming from here, across to here. That's the same as going from here, round to here. So now then, what I've got to do is I've got to take any signs that are the wrong way round and reverse them. So minus 84 is the wrong way round. We've got elements in the standard states making that, forming it. It's got to come round to here now, because it's got to go from there to there, which is the same as coming round from here to here. A process known as Hess's law, in that if it starts in the same place and ends in the same place, it doesn't actually matter about the route of the reaction. So minus 84 becomes plus 84, 0 becomes 0. This is going in the right direction, minus 1344, and this is going in the right direction, and we don't know what that is, so I've called that a question mark. So, and there overall it equals minus 2898. So, so 84 add 0, take away 133, add question mark, equals minus 2898. Okay, so I'm going to take the question mark and I'm going to leave it on that side, and I'm going to take all of these and reverse the signs. So minus 288 plus 1344 when I take it across the equal sign, minus 84 when I take it across the equal sign, equals minus 1638. That's the question mark. But that's for 6 lots of HF, 6 moles of HF, and it wants to know what's the enthalpy of formation for HF. That's the enthalpy, the amount of heat energy when 1 mole is produced. So if I make 6 moles, it's 1638, but for 1 mole I need to divide by 6 is minus 273, so my answer is B. Question 11. What is the temperature rise in Kelvin when 504 joules of heat energy are absorbed by 0.110 kilograms of solid iron? Specific heat capacity of iron is 0.448 joules per Kelvin per gram. If I've been given a specific heat capacity, the only equation I know with that is enthalpy change, or Q, equals MC minus MC multiplied by temperature change. So enthalpy change I've got is 504. Okay, absorbed, so it's a minus value. Minus MC delta T, minus MC multiplied by the temperature change, minus 110 grams. So remember, kilograms needs to be in grams, it needs to be in grams for this equation. So I'm going to multiply by 1000 to get kilograms into a smaller unit. 110 grams. 0.448. 0.448 is my specific heat capacity that I've been given, multiplied by the temperature change. I'm going to multiply these two out now, so minus 504 equals minus 49.28 times temperature change. So temperature change is minus 504 divided by 49.28, which is 10.2. 10.2 is 1.02 times 10 to the power of 1, so the answer is B. Calculate the enthalpy change in kilojoules for the dissociation of 1 mole of propan 1-ol. So 1 mole of propan 1-ol into 3 carbon atoms, 8 hydrogen atoms, and 1 O atom. So you're given the bond dissociation enthalpy, how much energy is needed to break a bond on average, mean. So when they're bonded to different kinds of atoms, then the bond enthalpy changes, but on average then this is what the value of these bonds are. This is how much energy in kilojoules per mole is needed to break these bonds. So what I've got to do is I've got to work out how many of these bonds are in this, because the enthalpy change, the total enthalpy change, is the number of bonds broken. That costs you energy. You need to put energy in to do that. Take away the bonds made, that gives you energy back out, and the overall difference is the enthalpy change. So the bonds broken in propan 1-ol. So propan 1-ol has got 7 carbon to hydrogen bonds. There's 7 H's there. That H is bonded to the O. The other 7 H's are bonded to C's. So 7 carbon to hydrogen bonds. In there I've got a carbon bonded to a carbon bonded to a carbon. So I've got 2 carbon to carbon bonds. I've got a carbon then bonded to an oxygen. So I've got one of those, and I've got an oxygen bonded to a hydrogen. If I add all of those up from these values here, it comes out as 4403. So my bonds broken is 4403. My bonds made is actual 0, because I've not made any bonds. All of these 3 carbon atoms, 8 hydrogen atoms, and 1 O atoms, they're all single atoms. They're not joined to anything else. So my bonds made is 0, so my bonds enthalpy change equals just bonds broken, 4403, take away 0, 4403 is answer C. Right, let's have a look at question 13. Let's have a look at the Maxwell-Boltzmann distribution curves to start off with. So, number of molecules up the left and energy along the x-axis. The higher the peak and the further the peak to the left is the lower temperature. The lower the peak and the further the peak to the right is the higher temperature, because more particles have a higher energy. Both curves should go through 0, through the origin, and they do, and neither curve should touch the y-axis, because always some particles, even though there's only a few, some particles have a high energy. This higher energy curve, so the peak is lower, but it should be shifted to the peak should be further to the right than the lower energy curve. So this is the higher energy curve here, and it should end up higher, so more particles should have a very high energy than the lower temperature curve here. The reason the peak shifted when the peak shifted to the left, the reason it's higher is that the area underneath the curve for both curves needs to be the same, because that represents the total number of molecules in the sample, and the sample hasn't changed. If you read down from the peak of the curve, so say for example P, that's the energy that most particles have at the lower temperature. R from the peak is the energy that most particles have at the higher temperature. However, just slightly to the right of the peak is the mean value, so that's the mean value of the particles' energy. The mean energy of the particles at the lower temperature is Q, and just to the right of the peak, S, is the mean value, the mean energy that particles have for the higher temperature. So your answer, which shows the mean energy of the molecules at the higher temperature, your answer is S. Which statement is correct for the higher temperature? The area underneath the curve to the left of EA decreases, so there's the activation energy. So more particles have the activation energy at the higher temperature. So as to draw the area underneath the curve, then more particles for the higher energy. The area underneath the curve, which represents the number of particles that have the activation energy or above, is greater than at the lower temperature. And so the area underneath the curve to the left of EA decreases. The area underneath the curve to the left of EA decreases. That is true, because the area underneath the curve to the right increases. The total area underneath the curve increases. No, the total area underneath the curve stays the same, because that represents the total number of molecules in the sample, and the sample hasn't changed. The activation energy decreases. No, the activation energy is the same. What actually happens is at a higher temperature, more particles have the activation energy, and therefore are more likely to have successful collisions. More molecules have the mean energy. No, in actual fact, the mean energy for S, for the higher higher temperature, there are fewer molecules. About here, that number here, for if you could read up from S and where it hits the curve at the higher temperature, there are fewer molecules than up from Q, which hits the lower temperature curve at a higher value here. So the answer is A. So we've got a rate investigation happening here. We've got 3 experiments. We've got 3 different chemicals, X, Y and Z. We've got the concentrations of each, and we've got the relative rate here. The reaction is 0 order with respect to Y, so that means that it's not affecting the rate at all. So if you double the concentration of it, let's say, then it doesn't actually affect the rate at all, because it's to the power 0 in the rate equation, so it's always equal to 1. So we can effectively ignore it. Let's do spoilers, and we can see order with respect to Y is 0, so it has no effect on the rate and can be ignored. We're going to look at experiments 1 and 2 first of all, because 1 and 2 has Z the same. So we always find 2 experiments where something is the same. We're ignoring Y because we know it's 0 order with respect to Y. So we'll look at experiments 1 and 2 where Z is the same. So what we do is we do 2 times 10 to the power of 3 for experiment 2 divided by 1 times 10 to the power of 3 raised to the power x, where x is the order with respect to chemical X, multiplied by 2 times 10 to the minus 3 divided by 2 times 10 to the minus 3 to the power y, where y is the order with respect to z. Those two are going to cancel, so 2 times 10 to the minus 3 divided by 1 times 10 to the minus 3 to the power x is 4 divided by 1, so we have the reaction rate 4 divided by 1 here. So that's 2 to the power of x equals 4. What number is that? Is it if it's a 0, then 2 to the power 0 equals 1. It's not that. If it's a 1, 2 to the power 1 equals itself, would equal 2. So it's got to be a 2. X is 2. The order with respect to x is 2. Now we're going to look at the other two experiments, experiments 2 and 3. Now nothing stayed the same apart from y, and we're ignoring that. So we're going to have to use these numbers, but we've got another piece of information now. We now know the order with respect to x is a 2, so we can do that. So for experiments 2 and 3, we take the 5 times 10 to the minus 4 divided by the 2 times 10 to the minus 3 raised to the power x, which we now know is a 2, multiplied by 4 times 10 to the minus 3 divided by 2 times 10 to the minus 3 raised to the power y, where y is the order with respect to z, chemical z, equals 0.5 divided by 4. Let's do some cancelling then now. This is 0.25 to the power x. 4 times 10 to the minus 3 divided by 2 times 10 to the minus 3 is a 2. 2 to the power y, and 0.5 divided by 4 is 0.125. So if x equals 2, we know that 0.25 squared equals 2 to the power y equals 0.125. That's 0.625 times 2 to the power y equals 0.125. So 2 to the power y is 0.125 divided by 0.0625, which equals 2. So y must be a 1. If it was 0, then 2 to the power 0 would be a 1. It's not that. If it were a 2, 2 to the power 2 would be a 4. 2 to the power 1 is itself, so it's a 1. Order with respect to y is 1. So we've got order with respect to x is a 2. Order with respect to y is a 0. We're told that in the question. Order with respect to z, that should say. Order with respect to z is a 1. And 2 add 1 is 3. So your answer is D. Question 16. Which statement about Kp is correct for this reaction in the gas phase? So Kp is an equilibrium constant. When you've got gases, it refers to pressure rather than concentration. But it's effectively the same thing as an equilibrium constant. Equilibrium constants only change if you change the temperature. That's the only thing that will change an equilibrium constant, change in the temperature. So A, the value of Kp is independent of pressure. That means that pressure isn't going to have any effect on the equilibrium constant. That's true. It's independent of pressure. It's only dependent on temperature. Temperature is the only thing that will change it, so it's independent completely of pressure. So I know A is right first of all. The value of Kp increases as pressure increases. No, only temperature will change it. The value of Kp increases as the temperature increases. That could possibly be true. We'll just have to check that out in a minute. The value of Kp is independent of temperature. No, temperature will change it. Temperature is the only thing that can change an equilibrium constant. Let's just check out C, and then we know it's A. The value of Kp increases as the temperature increases. So it's an exothermic reaction. That means that if you increase the temperature by Le Chatelier's principle, it will try and lower the surroundings. It will lower the temperature of the surroundings by not making more heat, reducing the heat, shift to the left-hand side. If it makes more of these on the left-hand side, the equilibrium constant, which is the pressure of these on the right divided by these on the left, will actually go down, because this value will increase, this one will decrease, and this one, the concentrations or the pressures of these divided by these determine the Kp. So the answer is definitely A. Table 17 shows the pKa value for two acids: propanoic acid 4.87, butanoic acid 4.82. First of all, I've got to convert pKa into Ka so I can make sense of those numbers. So pKa equals minus log of 10 of Ka, so pKa equals minus log to the base 10 of Ka. So these values, the pKa for propanoic acid 4.87 equals minus log to the base 10 of Ka. You've got to get rid of the minus sign first of all, so make both sides minus, and minus 4.89 equals positive log 10 Ka. Then you can get rid of the log by doing inverse log or shift log on your calculator. So inverse log or shift log of minus 4.87 equals 1.35 times 10 to the minus 5. So that's the Ka of propanoic acid. You do the same thing but for 4.82 for butanoic acid, and it works out as 1.51 times 10 to the minus 5. So now I've got the Ka's, the acid dissociation constant or the equilibrium constant for these two acids. The larger it is, the stronger the acid, because remember, a Ka, or an equilibrium constant, is the concentrations of the reactants multiplied together on the right hand side, the products that we're making, divided by the concentrations of the reactants on the left hand side. So the more products we make, the larger the number, the larger the Ka, the larger the dissociation constant, and the more products we mean, the more it's dissociated as an acid, and the more H plus it's made. So the larger the number, the larger the Ka, the stronger the acid. So butanoic acid is the larger answer, is the larger number, and butanoic acid is the stronger acid. So the value of Ka for propanoic acid is 1.35 times 10 to the minus 5. That's correct. The answer is C. Which element is in the F block of the periodic table? So you've got to find the F block, which is at the very bottom of the periodic table, and you'll find that plutonium is in that bottom block called the F block. So that's just identifying plutonium in the F block at the very bottom of the table from your copy of the periodic table. Answer D. Question 19. Which elements are shown in increasing order of the stated property? So first of all, atomic radius, so phosphorus to sulfur to chlorine. As you go across a period from left to right, the atoms get smaller. That's because they get increasing numbers of protons and increasing nuclear charge. So more attraction for the electrons that they have. They've not got any extra electron shells, so no extra shielding. So A is incorrect. They're getting smaller. The first ionization energy as you go across a period, for the same reason, because you've got increase in nuclear attraction from an increasing number of protons as you go left to right across a period, then the it's harder, more energy is required to remove 1 mole of electrons from 1 mole of gaseous atoms, and therefore the first ionization energy increases. Electronegativity, that means almost the power of them to withdraw electrons towards themselves. So how much they withdraw electrons towards themselves. Well, they're going to withdraw electrons towards themselves if they want those electrons, and sulfur is in group 6, needs 2 electrons only to fill its outer shell. Phosphorus in group 5 needs 3 electrons to fill up its outer shell, and silicon is in group 4 and needs 4 electrons to fill up its outer shell. So sulfur is closest to filling up its outer shell by gaining electrons. That will have the highest electronegativity, followed by phosphorus, followed by silicon, so they're actually getting lower. Melting point: argon, chlorine, sulfur. Well, these two are gases. Argon is a gas in light bulbs, chlorine is a gas, a green gas, and sulfur is a molecular, covalently bonded solid. So it's possible that it's D. All the others are eliminated. Argon, single atoms. Chlorine, diatomic atoms, two Cl's bonded together with a covalent bond, and then intermolecular hydrogen bonds. Chlorine is a larger atom than argon, so we'll have more electrons, stronger van der Waals forces, and therefore we'll have a higher melting point, boiling point, and sulfur will have a higher one still because it's got covalent bonds in a solid structure. So your answer is D. Which statement is not correct about the addition of chlorine to water? Chlorine can react with water to form an alkaline solution. No, it forms an acidic solution. It forms hydrogen chloride, which makes hydrochloric acid, which dissociates to make H+ ions. So A is incorrect. Let's have a look at the spoilers on the other ones then. B, chlorine can react with water to produce chloride ions and oxygen. Yes, in sunlight the chlorine reacts with water to make hydrogen chloride, so we can see it here. So it's made chlorate 1 ions. Those are chlorate 1 in 1 plus oxidation state. So +1 for the H, -1 for the 2. So the chlorine must be in +1, and they're called chlorate ions. Hydrogen chloride, as I've just said, then that hydrogen chloride gas dissolves in the water, dissociates to make H+ and Cl-. So that's correct. C, chlorine can be added to drinking water to kill bacteria. Indeed it can. Chlorine can react with water to produce chloride ions and chlorate 1 ions. Yes, we've seen that above. So your answer is A. Question 21. What is the formula of the main aluminium containing species present when aluminium oxide is added to an excess of water? Aluminium oxide, also known as bauxite, is insoluble. That's just something you've got to know. Aluminium oxide does not dissolve, so it's not going to form any of these aqueous solutions, and it's actually just Al2O3. There's no hydroxide ions there at all. That would be a solid that would be produced if you added, say for example, an aluminium salt to something like sodium hydroxide or something like that, before the sodium hydroxide was in excess. Your answer is D. It's an insoluble solid. What's the electron configuration of Cu2+? Well, first of all, copper loses an electron from its 4s level, and then it loses its second electron from its 3d level. So the answer is C. It's lost its 4s electron first, but it's lost 2 electrons, and then it's become 3d9 as it's lost 1 electron from its d level. The answer is C. Question 23. This is a rare question, this, using speed of light, Planck's constant and a wavelength, but it is on the syllabus. So you need to know energy is Planck's constant multiplied by the speed of light divided by wavelength. You don't really need to understand it as such, you just need to know that equation and be able to use it if necessary. So Planck's constant here, it's given you Planck, it'll always give you these values. Planck's constant 6.63 times 10 to the minus 34, speed of light 3 times 10 to the power of 8, and then a wavelength in nanometers, and nanometers 10 to the minus 9, so 600 times 10 to the minus 9, or 6 times 10 to the minus 7. You put those numbers in, and it works out as 3.32 times 10 to the power of minus 19. So your answer is D. So just something to remember if it comes up on the exam. Quite rarely it does, but you need to know that and be able to put the numbers in and calculate a value if necessary. The oxide of vanadium catalyzes the following reaction. What's the formula of vanadium containing intermediate formed in this reaction? You either need to remember it as V2O4 or remember that vanadium 4 is the intermediate. So from vanadium 4, vanadium oxidation state 4 with an oxygen. So oxygen is in minus 2. So that's 4 minus 2s is minus 8, and V2, 2 plus 4s makes plus 8, so it's in oxidation state for vanadium 4. So something to remember, that V2O4, something to learn. Question 25. Which catalyst is used in the catalytic cracking of alkanes, so making long chains into shorter chains? The answer is zeolite. That's just something to learn. which correctly represents an incomplete combustion of pentane. So complete combustion using a plentiful supply of oxygen, excess oxygen will produce carbon dioxide and water. Incomplete is going to make carbon monoxide and possibly some carbon as well, and maybe some carbon dioxide as well. But answer B, C and D are possibilities. A is complete combustion with no carbon monoxide made. So incomplete combustion here. D is making hydrogen. No, it'll never make hydrogen. It might make carbon monoxide. It might make some carbon dioxide with it as well. It might also make some carbon, but it'll never make hydrogen. So I'm between B and C, and I'm guessing therefore that one of them isn't balanced. Let's have a look at B. C5, 5 carbons, 12 hydrogens, 16 oxygens, 4, 5, 6, add 6 is 12. B doesn't balance in terms of the oxygens. Let's just check that C does. 5 carbons, 12 hydrogens, 6 twos, 12 oxygens, 4 add 2 is 6, 6 add 6 is 12. The answer is C. Question number 27. Which species is produced during a propagation step during the reaction of propane with an excess of chlorine in the presence of UV light? So the first step, the initiation step, will be that the chlorine will produce 2 chlorine radicals, 2 Cl dots. So don't be confused by that. The Cl dot then reacts with the propane and will substitute itself for one of the H's. So it's definitely not a H dot. I mean, you make HCl during the propagation step, but you never make H dot. It's not this, so you're going to get some kind of substitution of the H's with Cl's, but this might be formed in a termination step where 2 radicals come together to make a longer carbon chain. So it's not that one. It's between B and C where H's have been substituted. Now if you actually look at with B, C3H5Cl, you've introduced a double bond, so it's not got a double bond introduced in there. It's got to be C, where some Cl's are replacing some of the H's. Which compound forms a racemic mixture when reacted with KCN followed by a dilute acid? Well, let's do spoilers on this. So you're looking for the Cn minus from the KCN, the Cn minus, the lone pair on the carbon attacking the carbon of the carbonyl compound. So where the C double bond O is, the Cn minus will attack the C, and the double bond between the carbon and the oxygen will break. Electron pair will go onto the O, leaving a single bond, and then when it reacts with something like dilute acid, the H plus will react and turn the O minus with a lone pair of electrons attacking the H plus to make OH. So this C double bond O will become a CCN and an OH minus. But we've got to work out which one it is then. So A, incorrect, because you're going to get CH2 CNOH. So this C double bond O there, the C double bond O will become C with an CN and an OH, but there's 2 H's there on the C, so you've not got a chiral carbon in there, so you can't get a racemic mixture of 2 different enantiomers because you've not got a chiral carbon. B is a possibility. We think B is correct, so we'll have a look at that in a minute. This one won't have a chiral carbon because the CO will become an OH with the CN on the C, but you've got 2 methyl groups either side, so no chiral carbon, and again no chiral carbon on this because the C double bond O becomes an OH with the CN, but you've got 2 ethyl groups. So the answer is B. Let's just check B out. It's planar, so what will happen is there'll be an equal chance of the CN attacking from above or below to make 2 different enantiomers, and the CH will become, so the CO will become a COH with a CN, so that C will have an OH, a CN, an H and a methyl group. Your answer is Question 29. A tough question this. Use your understanding of bonding in benzene to identify the compound that has the most exothermic enthalpy of hydrogenation. So hydrogenation is when you add hydrogen across a double bond, to turn double bonds into single bonds by adding hydrogen across there. And it's an exothermic reaction. So the question is, which of these will react most readily? Which is the least stable and will react most readily and produce most heat in an exothermic reaction? Well, what actually happens is, well, let's have a look. This one's got 1 single bond, so that's definitely out because these have got, sorry, 1 double bond. These have got 2 double bonds, so you're going to get two sets of hydrogenation in A, B and D, where you've got two double bonds. That one double bond there rather than two double bonds will only react with 1 hydrogen, 1 mole of hydrogen rather than 2 moles of hydrogen. So it's definitely not C. The question is between A, B and D now. So what actually happens is when you get double bonds closer together, the electrons overlap and you get delocalization of electrons between the two bonds. So the overlapping electrons between two double bonds that are closest together and the delocalization of those electrons, the movement of the electrons between those two double bonds, creates extra stability. Stability means that it's not going to react as readily. You're not going to get an exothermic reaction as exothermic as if they're further apart. So these two are only separated by one single bond. So D and B are both separated by one single bond. A has got the double bonds furthest apart, so you get the least amount of overlap and the least amount of delocalization of electrons and less stability. Closer together you get more stability. So the answer is A, where you've got less stability and you're going to have a more exothermic reaction. Which compound is the strongest base? Another tough question here. So you're looking for something with a lone pair of electrons. So the ammonia, NH3, has got a lone pair of electrons on the N. So has methylamine, CH3, NH2. And phenylamine, a benzene ring with an NH2, has also got a lone pair of electrons on the N. Ammonium chloride is an ionic compound, so it's exchanged electrons between it's NH4 plus Cl minus, so it's not got a lone pair of electrons. So it's not B, it's between A, C and D. And what you've got to think about then is the availability of the lone pair of electrons. So not so much the larger the lone pair of electrons, we call it the more available the electrons are, but essentially it's how large the lone pair of electrons is, but you wouldn't say that in an exam. So what you've actually got is you've got NH3 with a lone pair of electrons on the N. Methylamine, you've got a CH3. Now CH3 repels electrons away, so it's going to increase the size, or rather make the lone pair of electrons on the N more available than to bond to an H+. So remember, a strongest base, a base is reacting with an H+, it's reacting with H+ acid. So if that's got a lone pair of electrons on the N and it's increased in size, got larger, or rather become more available, because the methyl group is repelling electrons onto that N to increase the availability of that lone pair of electrons, so it can act as a nucleophile and react with H+, then C is more basic, a stronger base, because of the increased availability of the electrons on that N. Phenylamine, a benzene ring, will withdraw electrons from the amine, from the NH2 on it. So actually that's going to lower the availability of the lone pairs of electrons on the N and make it less likely to be, make it a poorer nucleophile. So less available lone pair of electrons, poorer nucleophile, less likely to react with H+. That's going to be a weaker base. Your answer is C. So C, the methyl group, repels electrons, makes the lone pair of electrons on the N more available to act as a nucleophile and react with H+, which is what strong bases do. That's what bases do. Question 31, a tough question here. When you get any kind of amine, this is a tertiary amine, but when you get any kind of amine with an N in it, either a primary, a secondary or a tertiary amine, then it will react with halogenoalkanes. So haloalkanes like CH3Cl, something like that, and the lone pair of electrons attacks the C of the polar C to Cl bond, and the bond breaks between the C and the Cl. Electrons move on to the Cl and form Cl minus, and this joins on with a plus charge. So it's a nucleophilic substitution with a haloalkane, where the N, the lone pair of electrons on the N, attacks the C, the polar bond, the delta plus on the C, and the Cl minus is released. So this replaces the Cl using its lone pairs of electrons. This is a nucleophile, a lone pair donor, attacks the C, the delta plus on the C and the lone pair of electrons, the pair of electrons in the bond move on to the Cl to make a Cl minus with a pair of electrons with nucleophilic substitutions. Your answer is D. It's part of the process when you react any amine with a haloalkane, and it keeps replacing it in a series of steps until you end up with a quaternary ammonium salt used for cationic surfactants or detergents. Which polymer is least likely to be biodegraded after several years in a landfill site? Well, you need to know about amide or peptide links and ester links as well. So Kevlar and nylon have got amide links, a C double bond O NH link, sometimes called a peptide or an amide link. So they're polyamides. Terylene is a polyester, got a carbon to oxygen double bond O link. And all of those are formed when you react something like, so for Kevlar, maybe you've got COCl and acyl chloride with an NH2 and amine, and they react together to form a peptide link, and the same for nylon, where you've got an NH2 and a COCl, and they make HCl in a condensation reaction and an amide link. Or maybe terylene, you've got something like a carboxylic acid and an alcohol group forming a C double bond O ester link in there and making water in a condensation reaction. Or maybe again with a COO, a carboxylic acid group, with an acyl chloride group, a COCl, and making HCl. But in any case, these have got either amide links, NHCO, or ester links, COO, in there, A, B and D, and you can reintroduce water. So when you make them, you make water, but you can reintroduce water, a process called hydrolysis, breaking bonds using water, and maybe you've got a little bit of acid in there to catalyze it. But polythene is an addition polymer. So what's happened is the double bonds between the carbons have broken and made single bonds and a long chain of carbons. And those carbon bonds are very, very strong. So that backbone of carbon to carbon single bonds formed when an ethene forms reacts together in addition polymerization reaction to form double bonds forming single bonds. Those single bonds are very strong and they won't be hydrolyzed by water, they don't react. Question 33. Which structure shows 2-amino-butanoic acid as a zwitterine? So a zwitterine has the carboxylic acid group, the COOH. The H is lost and it forms COO minus. The H is lost as an H plus and leaves behind, instead of COOH, as the H plus is lost, it leaves COO minus, and the H plus joins on to the NH2 group and forms NH3 plus. So we're looking for an NH3 plus and a COO minus in a zwitterine. So we can automatically rule out C because it's got no pluses and minuses. We can rule out D because it's got a minus on the NH3. That should be NH3 plus and that should be COO minus. So C and D are automatically wrong. Let's have a look at A and B. NH3 plus, yes, that's correct. COO minus, yes, that's correct. NH3 plus, correct. COO minus. So it could be A or B. But which structure shows 2-amino-butanoic acid? Well, you should know that a carboxylic acid group, and this bit has been the carboxylic acid group, this has been the COOH before it's lost the H+. This bit is carbon number 1. So this bit's carbon number 1 because it's at the end of the chain. Aldehydes, carboxylic acid group, nitriles with CN at the end of a chain are always carbon number 1. So if that's carbon number 1, then the amino part, the NH2 before it's accepted an H plus and become NH3 plus, is on carbon number 1, 2, 3. That's been 3-amino-butanoic acid. Carbon number 1, carbon number 2. The amino group has been at carbon number 2 before it's accepted the H plus. So the answer is B. Question 34, a tough question because we've been given an organic reaction pathway and we've got the product and we've got to work back all the way to work out what the alkene was right at the beginning. So let's have a look at this here. So I've got CH3, CH2, CH there, CH3 here, CH2 and then an NH2 at the end. So before that there's been a nitrile, so this has been a CN, a C there and an N there. And what's actually happened is the C and the N have had, with lithium aluminium hydride, you could use sodium borohydride. In some way or another you could use hydrogen gas with a nickel catalyst. There's various different ways to get hydrogen across this nitrile here. So that's been a CN, and we've added H's across the CN across the nitrile. So let's draw it again. It's been like that, a C there with an N, and then hydrogens have been added across the CN to make CH2NH2 by using this chemical, this lithium aluminium hydride or sodium borohydride you could use instead, or you could use hydrogen and nickel. What's happened before then? So what's happened before this? Well, this CN here has reacted with a halogenoalkane, something HBr. There's been a Br there, a Br, and the CN has joined onto the C. It's been a CBr. That C there has had a Br here, and the CN has come and had nucleophilic substitution added onto the C, and the Br has been replaced. So there's been a Br there, and the Cn minus from potassium cyanide, the Cn minus with the lone pair of electrons on the C, has attacked the delta plus of the C of the CBr, and there's been nucleophilic substitution. The Br has been replaced. So before that it's been C with a Br, and as I say, the Cn has attacked that C. That's going to be delta plus C, delta minus Br, because the Br is more electronegative than the C and forming a polar bond. And as that nucleophile attacks that C, the Br has been replaced, and then you get a Cn joined to that C. Okay, what's been before then? So before then, that Br has joined across a double bond. There's been a double bond, and the double bond has been here. This double bond has been here because then an H has bonded onto there, an HBr. You've used HBr to add across a double bond. So before that, it's been but2ene. Another possibility is that it could have been but1ene, I suppose, with a double bond here, but but1ene doesn't appear on the list. So my answer is A.